Uh, why don't we start the chemistry aerosol and full atmosphere model working meeting. So each of the presentation, you have 15 minutes and try to be done by a few minutes early to allow time for questions. So we have a bit of a tight schedule. Uh, for the in-person presenter, you can either use a laptop up here or feel free to just share from your own screen. Either is fine, whichever you would prefer. It's maybe easy to use your own screen, but so with that, maybe we can get started. Marcin, you're here. Do you want to go ahead and share your slides?
Sure. Is that visible?
Yes, and we can hear you fine.
And you can hear me fine. Okay. Shall I get started?
Yes, please go ahead.
Okay. Okay, so today, well, yeah, first of all, thank you for giving me a spot to talk here. It's nice to be here talking to all of you across the pond. So today I'll be talking about the variability that we have been seeing in the D&E region as simulated by Wacom-RR, the regionally refined version of Wacom. And just to give a little bit of background, the D&E regions exist in the mesosphere, lower thermosphere, and ionosphere system, roughly between 60 to 100 kilometers. And this part of the atmosphere has historically been struggling to be represented by models, which means various things. And one of them is poor forecasting capability. And this part of the atmosphere is quite key as it can couple to regions from above and below, impacting things such as lower atmospheric climate and upper atmospheric space weather. And it is also driven by processes from above and below. And the various interplay of those processes and what processes dominate at different stages is not fully understood. So this is what we've attempted to do here at Leeds using Wacom-RR. So just to give a little bit of background on the model. So it's essentially the recently developed Wacom with spectral element dynamical code that has regional refinement capability built into it. So this is Lauritz and Peter's paper showing the development of the grid, what the grid looks like. Essentially has all the capabilities of spectral element Wacom, but with the refined mesh. The grid is built using the VRM editor software, and we've tested various things here in Leeds, and happy to shamelessly plug in that we've had the acceptance of our recent paper, which shows Wacom-RR results over the contiguous US in using the CONUS grid. So you can find the open archive version of the paper from the QR code whilst it's currently in the acceptance stage. The thing I'll be talking about today is a model we've been developing called Scandi-RR. So it's just a picture of the grid to the side. The grid has a 1/8 of a degree horizontal resolution over Scandinavia, as can be seen, and then of course 1 degree grid outside of the nest, where you can see the high resolution region here, and then steps out onto 1 degree. It's 135 vertical levels with approximate vertical resolution of 2.5 kilometers. In the MLTI, time step of the model is 3 minutes and 45 seconds. And just as we've been developing, we've been running the model from mid-March to mid-April using historical forcing, and the gravity wave parameterization that is active globally has been switched off over the region mentioned here, which basically contains this entire nest region as well as some parts outside of it. So just to show some results that we've been having, so some of you might have seen some of this already. So we've managed to get some very interesting structure and wave patterns coming out from the grid and variability, where this is showing temperature and February conditions from roughly the stratosphere all the way to the lower thermosphere. And you can see that there's all these very nice coherent wave patterns that that seem to persist up to about 65 kilometers, and things then go a bit more chaotic. Similar can be seen with vertical velocity, where these nice coherent structures persist until about 65 kilometers and then appear to be destroyed above that, where the field is more chaotic. And then with electron density in the D and E regions, so this is just isolated for daytime conditions, you can see that as the atmosphere is in daylight, there's quite a lot of structure that's seen in the electron density as well. And you can see some signatures of those orographic like waves at the lower point here. So one of the things that we are interested is the new IceCat 3D instrument. So this is an array that is spread across multiple sites, and it was supposed to be switched on this year, I believe, or in the recent has not been switched on yet, but we were planning on using WACOMAR results to help interpret IceCat 3D data. So just one thing that we've been trying to do is to see what would IceCat 3D see if we sampled WACOMAR in the region that IceCat 3D is observing. So this is just our first pass approximation at doing this. So here gives you an idea of some of the points that IceCat 3D may probe. So this is looking at a 30-degree elevation angle from the Earth, and some of the spread of points that this would produce. The viewing window and the resolution are changeable parameters. So as I understand, the idea is that different users can request different fields of view and different resolutions for depending on the science question that they are studying. But for this purpose, we've assumed that we're sampling WACOM on the widest viewing angle of IceCat 3D to contain as many points that we can from the high resolution region. So this here on the right just gives you an idea of what points are included in a 30-degree elevation angle as you change in altitudes. So roughly at 100 kilometers, it gives you a viewing, a radius of between 100 to 150 kilometers in the horizontal. But these were just some things we have been looking at coming out of the model. So this is looking at temperatures in March conditions. Here's 80 kilometers and 95 kilometers, and you can see that there's again a lot of structure that would be picked up by the instrument, and a lot of wave-like patterns that have variability on timescales from tens of minutes to several hours. In vertical velocity, you can again see that the field is a lot more chaotic, as we've seen previously, and if this was IceCat 3D, it would be picking up quite a large range of variability, varying quite rapidly, with the dominant modes, occurring from again tens of minutes to order of several hours. Again, just looking here at the electron density. So this is again set up for daytime conditions. You can see that there's quite a considerable amount of variability seen in these regions. So 80 kilometers is roughly at the top of the D region, base of the E region, and 95 kilometers is situated right in the middle of the E region. And you can see that there's considerable amount of variability seen in the model that would be likely picked up by the instrument. So one of the things that we would like to do is to try to understand what is driving some of this variability. such that such observations could be interpreted. So this is just showing the electron density, number density. This is the average of all the data in the ISCAT 3D field of view. So it's basically at each height quoted here, 110, 95, and 80 kilometers. The solid line is the average of all the points at those heights, and then the shaded region is the confidence interval, essentially showing twice the standard deviation. So you can see that there's this very strong diurnal variability. So there's this strong day-night variation at all of these heights. This can be visible at all of these heights. There's this subseasonal variation. We can see that there's this very steady growth for here that we're looking very steady growth and then decay. Something similar is seen as heights below. And then we can see that at heights such as 95 kilometers, this is really short scale variability that we can see on the orders of, again, several tens of minutes to hours. That is most strongly visible at 95 kilometers. So that's in the middle of the E region. So we want to understand what is driving this variability. Well, there are a few things that can quite easily be answered. So you can, at 110 kilometers, this peak actually arises at midnight. So around midnight. So this is, you can tell that this is driven by auroral activity. You know that during the day, these peaks are centered roughly around midday. So that will be driven around photoionization in the day. And then the thing we want to understand is, what is photoionization of what, and what are those processes governing that, and then also what is driving the larger scale variability. So here, this was just something we managed to take a look at. You can see that actually the pattern correlates reasonably well to the KP index. So you can see at the height 110 kilometers, the variability of electrons matches quite closely to what the KP index is doing. And then there is this lagged variability that we see here at 95 kilometers, which we're still trying to understand. But overall, it gives you an idea that the subseasonal variation is likely driven by essentially variations of geomagnetic activity as described by the KP index. I'm just noticing the time, so I'll be very brief and succinct. One thing that you find is if you correlate the electron density to nitric oxide, you get a very strong correlation of about 0.98. So this time series that you're looking at here is just the daytime values over the mid-March to mid-April period. This is at 95 kilometers. And it's known that photolysis of nitric oxide is dominant source of electrons at these heights. So it's quite nice to see that in the small scale variation correlates so strongly between nitric oxide and electron density. So the question that's left to answer is what's driving the NO variability? And the likely culprit, of course, is gravity waves, since that is what the model is attempting to resolve as it goes to higher resolutions, but we are still in the process of trying to prove that. So in summary, WACOMAR produces small scale variability, which can be seen in temperature, vertical winds, and the electron density, as well as other fields. ScanDRR, the model over Scandinavia, produces small scale variability, which we notice in electron density, which we have managed to correlate to NO variability. And then the next step that we want to do with this is understand what is controlling the variability of nitric oxide. So I'll stop here and I'll take any questions.
Thank you. Are there any questions? Hey, Martin, I have a question on the, because you showed the electron density at 80 and 95, I was wondering when ISCAT 3D is up and running, will it measure wind in that altitude range, or is only electron temperature there, or I mean electron density there?
So I don't know for sure, but it is an incoherent scatter radar, which I believe has the capability to measure winds. But I mean, I'd have to double check, and I can email you afterwards to give you details of exactly what it will measure. But I believe it should be able to do that.
Great, thanks. Any other questions? No. Thank you again for the presentation, and I think next will be Rafa will give a talk on implementation of the short-lived halogen in CSM. Want to share your screen?
Okay, so thank you very much. So I'm Rafael Fernandez from the National Research Center in Argentina, and I've been presenting the development of short-lived halogen chemistry and implementation in CSM2. This has been performing in cooperation with the Madrid group, the Madrid halogen team, led by Alfonso Saiz Lopez and many colleagues there, and a bunch of people here, mainly at NCAR, Dakini Son, Francis, Luisa, Simon, Ben, many people help us in working on this. So I'm happy to show for the first time, this is the final release of the discussion paper. I was supposed to answer the discussion this month, and I asked for an extension until the end of the month so we could finalize some things with Francis on some things around here, but everything has been advanced. The code is already available for people to hang around and take a look. So most of you are more familiar than me with all these configurations and stuff. So basically, those are the new concepts that we have implemented in the new CSM 2.2 SLH code. Basically, most of the results I will present today are based on the FCNACH and FCHIST SLH configurations running in 2 degrees using Trop Stratman for SLH scheme. So I would like first to perform some rapid update of all this work that took more than 10 years since I joined Alfonso's group in Madrid, Toledo by that time. The Saiz Lopez 2012 and Ordóñez 2012 papers were just submitted when I joined the group. And since then, when we presented the first emission inventory of chlorophyll A-driven and surface temperature-driven emissions of halogens, and the first estimation of the impacts on tropospheric zone, we have been addressing many and several aspects of halogens and how they interact with different oxidants in the troposphere, how they change the Hox-NOx ratio, the methane burden, the aerosol burden, mercury chemistry, ozone depletion substances with natural and anthropogenic contributions and everything. So all of this has been reviewed in a recent paper just published at the end of the year, this year. So here we go. So basically, these short-lived halogen species have short lifetimes, so they are not transported directly to the stratosphere, and differing from the CFCs and halons. So the conversion from source gases into product gases at different heights and how they perform recycling reactions, they interact with the clouds and wash out dry deposition, wet deposition, and all these processes are mandatory to be considered. And with that, we can, the original requirement was, there was a need to increase the total bromine in the stratosphere to make all models available with observations. I mean, to be in matching the observations. And this was expected to be due to the natural contribution of these short-lived halogen species emitted mostly from the oceans. So since then, we work in different projects. So here on the top left, this is the vertical profile of brominated halocarbons emitted from the oceans and how they are transported all the way to the stratosphere within the tropics. So on a global average, there is 5 ppt bromine injections, and we have made all of that. All these results that I'm presenting at this moment are from using CSM1. That was all the development was done with CAM4Chem. And with that, we could reproduce. And I remember the first time I came here in 2015, late 15, to work with Atkinson, they resulted in increase the ozone hole depth and the ozone hole size by a significant amount. And then in addition, to make compatible of the observations with this iodine scheme, it was required to have some iodine recycling reactions and photochemical and degradation of the higher order iodine oxides. And with that, we recognized that that was only consistent with an injection of iodine, which, regardless of the different scenarios that we could consider or the chemical scheme that we have in the model, they were always larger than the best estimate of WMO report of injection of iodine into the stratosphere. And with that, we later showed that this could also increase the size of the Antarctic ozone hole. Moving into the troposphere, so we showed that doing climate simulations that all these halogen emissions, and in this case, the role of iodine was really important, reduced the ozone burden by approximately 15%, regardless of the scenario moving into the future. And in addition to that, because of that ozone reduction, there is a reduction also in OH. So we have more chlorine, it will destroy more methane, but then at the same time we have less OH, and that will reduce the methane lifetime. That will increase the methane lifetime, reduce, and with that we found that including halogens finally end up increasing the lifetime and the burden of ozone, of methane. And I know Ben is presenting later some results also on this using the new CSM2 version. So this is like the final summary of all the impact of halogen emissions. They are coupled with air pollutants, and for sure they affect the abundance of methane, ozone, aerosols, and many other short-lived climate forces. And with that, they impact on the global relative balance on the top of the atmosphere. And we found some interesting effects of this chemistry, which is now implemented in CSM2. So basically, which are the processes, like going more into technical and then to show some CSM2 results and comparisons. So we have the degradation in this yellowish color of long-lived species, either CFCs or halons. We include also methyl bromide and methyl chloride, which have longer lifetime than short-lived halogens, which are larger than 6 months, but then not as long as some other of the CFCs. We included all natural and anthropogenic emissions of several halocarbons, brominated, chlorinated, and iodinated halocarbons that are that have a photochemical lifetime of about 6 months. And then, in addition to these photochemical reactions, we also include some recycling online computations of bromine and iodine sources. Bromine occurs mostly on sea salt aerosol recycling, and iodine mostly on the sea surface. And I will show some particular details in the next slides. And in addition, for sure, we made all the chemical partitioning among all the iodine species and bromine species, and how they independently can be removed and washed out in the model. So this is basically in the model implemented in different routines and different sections of the name list. So these are all the species that we included some offline emissions. For the particular case of iodine, HOI, and I2, so we included them as they seem to be like offline emissions. But once we read those variables from the name list, then we force them to 0, and then we compute and replace them online on the model. There is a specific routine doing that. There is also some changes on some boundary conditions of some of these short-lived halocarbons for which we don't have yet emissions inventories to include. There are also some updates in the absorption cross-section. Atkinson was the person leading all this and how to implement it using the lookup table approach. We then also updated all the dry deposition schemes and extended all the underlying species were initially considered in any chem CAMCHEM standard mechanism, and all the underlying species are the new ones that we include in this scheme. And same for wet deposition. We use the NEO scheme, but also implemented for some of them the free regime approximation, which is a non-stoichiometric zinc that is included in the chemical mechanism. And we also need to include some scaling factors to tune some of these recycling efficiencies in the model, which is now implemented. So going into some of the details, so if you look at these reactions here on the top left, they are non-stoichiometric for the case of chlorine and bromine. So they represent every time one of these gas species collides with a sea salt aerosol, can uptake a halide ion from the sea salt aerosol, which is considered to be an infinite reservoir. And this strong emission is strongly dependent on resolution, and that's one of the most difficult stuff to do the tuning, and when changing from 2 degrees to 1 degree, for example. For the particular case of chlorine, this is also happening like the acid displacement reactions, which release chlorine in particular. And for the case of iodine, so ozone is deposited into the oceans, assumed to be in deposit, and react with aqueous iodide, whose concentration depends on Seifert temperature. And then the release of molecular iodine or HOI depends strongly on wind speed and concentrations of ozone. So this has resulted, as this is completely online, in a chemical feedback that has buffered the levels of ozone due to the increased emissions from the ocean, as we have been able to confirm using ice core observations in Greenland and also some tree rings. So these are the final scaling factors that we have for the different configurations. I just put this slide because when I first implemented this, I say, I'm cheating. How can I be including this? And then I was aware that many people is doing and including scaling factors in different places because we have plenty of parameterization. So I was more relaxed and I say, okay, we need to try to reproduce all the 10 years of work using an old version into this new one. And have these now scaling factors included in the name list for people can rapidly change them and not be getting into the law. So here, this orange color showed that the long-lived species on the top are the dominant sources of inorganic chlorine in the upper stratosphere, which is expected. But then if we go to the lower stratosphere, this is the tropical, this is a global mean, sorry. We can see that not the anthropogenic contribution of short-lived halogens is also really important. But then within the boundary layer and the lower troposphere, the contribution of chlorine from sea salt recycling are the dominant sources that we can get on a vertical scale. If we look at the same for bromine, we can also see that in the upper stratosphere and the middle stratosphere, halogens dominate on methyl bromide, but then in the lower troposphere, in the lower stratosphere and all the upper troposphere, the main sources are from bromoform and bromomethane, and in the boundary layer, once again, the sea salt recycling contributions are the dominant ones. So with this, we have now, and I remember Doug Kinnison saying, I love this figure, saying we have a complete representation of organic and inorganic partitioning of bromine, chlorine, and iodine in a model from the surface to the top of the atmosphere. And this was great. This, the different symbols are FC HIST and FC NACH configurations. So that's something also really good that in CSM2, we got with the tuning factors to get all of the configurations to be like really similar one to the other. And on the bottom, this is the tropical mean, source gas injection in blue, and we compare with the latest WMO values of how much short-lived halogens are being injected to the stratosphere, and the model really agrees well with observations. With that, just to show some CSM2 results, this is the impact of comparing a halogen versus a no-halogen simulation, the difference in ozone. And we can see that particularly in October in the Antarctic ozone hole, the contribution is significant, but it can also affect all the lower stratosphere where this contribution was known to be the dominant one. And here on the right, I won't go into details, but are the loss rates split by the different chemical cycles. So the bromine-driven, the chlorine-driven, the iodine-driven, the Hobbs and Ox-driven cycles are all compensated when this halogen chemistry is included. So where are we now? And that's why I've been here dealing with Francis and many other people. So this is the CAM6 version that we have on the right. And when I asked for the pull request after having all of this, they say, why are we keeping this if this code will no longer be available? So we start working with that with Francis, importing everything to the CAM6 development branch of the code. And we have it done. I've been testing the first results, and this is really important. This is just one of the questions I need to ask. I do need to answer from the review. So we have all the repository in my personal GitHub, but it's not in the trunk of the code yet because this is CSM 2.2 SLH version. And how can we make sure that this will be available to the community? So then we need to put everything in CAM6 development. So we've done it. So these are just some rapid comparisons. So this plot is when we switch from the CSM 2.2 to the closest CAM6 development version available by that time. And this is the final results I've just performed this week with the latest version. Francis has put it into the almost the latest. I don't know if it's 142 or 44 tag here, but okay, it's really being reproducible in all cases, all the vertical profiles of iron species. So not to take too much longer. So basically, what we are willing to do right now is to have a fully coupled BW or BC configuration. So in CSM2, this was with Bob. Now in CSM3, the ocean model is MOM, but there is no coupling between CAM6 with MOM. It's only CAM7 physics, which has been tuned with MOM. So what should we do? Should we include POP into the CAM6 development branch? Should we make a tuning of CAM6 development with CAM6 physics with MOM? I don't know. These are the questions that I wanted to answer with colleagues here during this week. Just a final comment. We are all aware about all these issues that have been facing NCAR in the latest due to the new government. And this is a gracias totales to the NCAR staff, okay? So that's, for an Argentinian, gracias totales is much, much, much more than thank you very much, okay? So it's been really great to have all the contributions. In my case, from the CSM community, but I can imagine NCAR for the whole community, atmospheric community, it's an awesome place to be and to share with. So thank you very much.
We can maybe take one question for Malcolm.
Thanks for your presentation. In simulating the ozone depletion with your model, are you also simulating the lower stratospheric ice clouds or ice particles within the model, or are you treating that with the parameterization? Yeah.
Everything that is occurring in the stratosphere is exactly as was originally implemented in WACAM by Dickinson. The only thing is that in addition to the heterogeneous recycling reaction of inorganic chlorine and bromine, we also added inorganic iodine species with equivalent gamma factors that we have for other species. But it follows exactly the original implementation. Okay? And just for everyone, I'll be here until the end of the week. So any discussion you would like to have about this code, I'll be happy to meet with any of you at any time. Thank you.
Thank you. In the interest of time, I think we should move to the next talk, which will be given by Ben Gobert, and it's assessing the drivers of the temporal variations in methane loss.
I need to stop sharing, isn't it?
Yes, you need to stop. So this Ben can.
Right here.
Hi, thanks. Good morning, everyone. Thanks for the introduction, Rafa. So I've been using the CSM2 SLH in this presentation, so a lot of the details were nicely presented. This is some work I've been doing with collaborator in University of Arizona with NOAA project and Shuo Chen, that is a Ralph Cicerone Fellow of AECOM from Purdue. So just a little background on the methane budget. So methane is emitted from a large variety of sources, from fossil fuel to agriculture, waste, and many other things, including biomass burning, and some natural or indirectly natural from wetlands and inland freshwater sources. And the thing as opposed to CO2 is that the methane loss is entirely controlled by chemistry, and 90% of it is hindered by tropospheric OH. And so this is the main interest here, because you can see here the spread in emissions and chemical loss is very large. And the only way to constrain emissions in a way that would be acceptable for predicting future persistent climate, you would need to reduce OH. And because of this 10 years lifetime, you might wonder if those variations that we see at 5 to 1, annual to decadal changes in methane concentration might be due to chemistry. A lot of it is driven by chemistry, by emissions. We know that recent acceleration since 2006 is driven by tropical emissions, which point to wetland and agriculture in the region, like rice, for instance. But there are a lot of studies that suggest that OH might be playing a role. Could be, for instance, like the COVID-19 lockdowns led to extreme reduction in NOx emissions, which led to changes in OH, or the extreme fires in Australia that led to OH anomalies at the hemispheric scale. There are papers almost every week on the subject, but sometimes the chemistry is not really well understood. And this is because OH is very central in tropospheric chemistry. So here you can see one of the actually used in CSM, a superfast mechanism that was designed to be a very low set of reaction. Geoschem, that is widely used, 3D model, and a box model that cannot even be run in 3D. And in this study, they compared the interaction of all the different chemistry, and OH is the most important species in all. So it is very important, and it will depend on the errors related to all the other species involved in the sources and sinks of OH. There are constraints from messy chloroform, and the messy chloroform decay in the atmosphere can give you a global OH, and that's the only metric we can have because of the very short lifetime of OH. And uncertainties are considered to be 10%, so 10% for global OH every annual. So using the same metric, chemistry, climate models would have an uncertainties of around 20%, which is way too much. And they tend to overestimate OH. There are discrepancies with the messy chloroform, so-called observationally derived estimates. There are also differences when you're trying to get to the spatial distribution. So this is the ARChem MIP. And so one of the latest MIP in chemistry, and every single model is outside of the observational range because of the OH issue, which is illustrated here in terms of CO. This could be due to CMIP6 CO emissions, and I will talk about it, but clearly we're talking about like two different distributions here, and it's not really accepted. So the vision is to provide, to develop a system where you would have methane emission, if possible, with process models and interactive chemistry, so that we can include and quantify the chemical feedback of methane and 2OH and their feedback into across the Earth system involving all of those chemical species. And eventually include fire, wetland, soil emissions of methane or all of these species. Like for fires, you would have all of them. I mean, most of them. And so here is what you normally do with assessments, estimates, and this is getting posterior fluxes from NOAA. So they're doing inversions using methane and methane isotopes to constrain fluxes, and we just input these monthly fluxes into our model. So you can see they're actually fairly similar, except that you would have much difference in the longitudes that are not resolved in prescribed fields. So when we heard about the Chile paper about the impact of SLH on ozone, literally were very interested right away into getting this OH bias issue to be resolved. And so we've been collaborating with RAFA using this code, CSM2 SLH. And so here's a comparison of TS1.2 versus SLH. And indeed, we reproduced those results that are compared here against ATOM. And so in the northern extratropics, you reduce ozone, which the main impact of using SLH is reducing ozone, and so then you would reduce OH, especially in the winter and spring of the northern extratropics. And it shows improved results for those restrictions. So one of the things here is that here's the observational estimate for tropospheric ozone, and this is what you get with TS1.2. And then the SLH simulation, we are now in this region where we tend to overestimate ozone, but having a much better methane. So, you know, if you're outside of this range, you cannot simulate methane accurately. The other thing we found is that posterior emissions from earlier studies using MOPIT were much higher. And you need to use higher CO emissions from anthropogenic sources in order to actually reproduce the satellite observations. So here is TS1.2. When you have the SLH, you're reducing the bias, and then when you add SLH and posterior CO emissions, you actually now feeding the satellite observations. So now I'm moving on to 20-year simulation, where I'm trying to reproduce that large increase in the methane over that period. So we're using 2002 as spin-up, and then we go all the way to 2023 with two different SSPs after 2015, and the NOAA Carbon Tracker now 2025, and we updated the anthropogenic emissions to CAMS Mosaic, which include updates over China and the US to have better trends, and we're still using the posterior CO from the previous study and FIM 2.5 for fire. And in addition, we're also doing the CMIP7 input data set, so it's only anthropogenic and fire emissions are used here. Everything else being the same, including methane emission. And in this case, we increase the CO emissions only by 30%. This one. Yeah, and I'm not going to talk about this. So here are the differences in emissions. So, so our posterior is still higher than the new sales emissions for all the regions. And the orange and magenta are the fire emissions, and here is thin in the tropics. It's much higher than what the BB4 CMIP GFED 4.1s estimates are. Also in the southern tropics, and it tend to agree in the southern extratropics. In the northern extratropics, they are fairly similar, except that GFED is capturing the Arctic 2021 fires, which are much higher magnitude and usually higher peaks in the summer time. So it's well known that, and actually previous work is showing that tropics is, the fin is too high in the tropics, and especially northern. So in that region, the northern tropics is hotspot for other emissions. But we also know that GFED.1s, 4.1s is underestimating fire in this region, especially in the spring. So you get 500 teragrams of CO reduction between our initial CSM methane simulation and the one with initial emissions, which is quite significant. So here I'm decomposing the MOPIT time series over the 20 years, and it's for the trend and interannual variability. And the blue one is CSM methane, and then the CMIP7 in salmon, pink, and brown for the one with higher CO. And you can see an offset in the background where the CSM methane tends to be a bit too high globally, but overall, while reproducing the northern extratropic CO trends over the period, while the CMIP7 emissions are too low and giving you too low background. Here is for interannual variability. You can see that these fires are very much in line with the MOPIT observations. They do overall very well in reproducing those internal variability, which will be interesting later in future work. But if you look at the seasonal evaluation, so this is 20 years differences with MOPIT for the 4 seasons, and the seasonal cycle for the also 20 years. You can see that we tend to overestimate the spring time, but overall the pattern, it looks very good in our CSM methane simulation, while the one from CMIP7 are a bit out of phase and tend to underestimate the spring emissions. And then if you look carefully, the springtime emissions, so might be due to fires, are actually well reproduced in fin, but in Southeast Asia, springtime emissions, then fin tends to be too high, while the BB4 CMIP might be too low. And the background here in anthropogenic is solved when you increase the anthropogenic emissions by 30%. So the truth is in between. It's nice to see the sensitivity. So we're looking at airborne field campaigns from CHORUS and ECLIP over East Asia. And so now I'm also adding methane to CO and ozone, and you can see that the CMIP7 has very low methane compared to CSM methane, which might be due to the fact that there is too much OH in this simulation. CO is well reproduced, and for both of them. And the CSM methane is doing better than the SSP scenarios. So now I'm looking at actual methane data at the surface. I'm using the NOAA marine boundary layer side and applying the same algorithm that they use to calculate the growth rate, so that I can compare the observations and the different simulation in apple-to-apple comparison. And you can see that the SSPs are overestimating the methane values that the CSM methane is reproducing. The NOAA observations very well for all the different parts of the globe, while the use of CMIP7 forcings is led to an underestimation of methane despite using exactly the same emissions for methane. And so we are also reproducing the atmospheric growth rate very well, where the negative or low atmospheric growth rate 2003 to 2006 are actually quite well reproduced by the CSM methane simulation. And then after 2007 is only positive growth rate and acceleration towards the end, 2014, 2020, 2021, that the CSM methane simulations are able to reproduce with low uncertainty, especially compared, even compared to the prescribed with observation era, which reflects differences in the network. So so now I'm redoing this figure. So here is the sensitivity due to lightning, and this is a difference in external forcing with the impact of zero. And so we can see that CMIP7 forcings are outside of the range, which explain why the methane is underestimated. We also check the OH budget and see if how it compares to the Bosolasco et al. Paper. She is meeting last year these results, and the Lieveld et al. That has a different organic chemistry mechanism. And they all agree on having a primary OH production of around 40%. Actually, this is low here, but which shows that the recycling probability would be 0.6, which means that global and annual OH actually don't change much compared to perturbation. The secondary recycling of OH is more important and tends to buffer compared to perturbation. We still need to understand why the values are lower in terms of the source of OH in this simulation, because it's also a difference between CSM2 and CSM1 settings, although they're using probably very different input data sets as external forcing. So now we can compare the CMIP7 emission scenarios, the scenario, and you can see that it's mainly driven by the changes in CO emissions, where you get more tropospheric loss in the CSM methane simulation, which reduces OH, while in the CMIP7 scenario, then you will have higher methane oxidation, and that's why we're not simulating methane correctly. And this feedback to all the other families interacting with OH. With C2 as shorter species, shorter lifetime, so it would be impacting the same way, where the one with longer lifetime are impacted as a result of those perturbations. So quickly, I wanted to show new results where we started to do ensemble to assimilate tropomi, methane, and CO observations. And we did one in particular where we're using 30 different nudging to ERA5, where we consider no nudging to temperature and Q, and then gradually increasing the values to very strong nudging to ERA5. So those are the strengths. ERA5 is available every hour, so that gives you a range of relaxation time. And we also used different ensemble using wetland emissions from 30 different observational data set and all machine learning constrained and inversions of wetlands, and those are also constrained with observations, and also a chemistry ensemble where we have different lightning emissions. So one of the things we noticed is that you get a different CO emissions even though they're the same. And so this pointed to Megan response to dynamic, and you can see the green here is the different nudging, where these ones are the strongest nudging to ERA5. And so using something that is weak nudging to a strong nudging, that can give you up to 150 differences in Megan emissions, even though the vegetation is prescribed, the LAI are prescribed. And here you can see the spread due to chemistry, which is mainly driven by lightning. But they all have the same Megan emissions because the dynamic is the same in this case. So the other thing that we thought could have an impact is the specific humidity, and you can see here the spread where it gets drier with stronger nudging to ERA5, which gives you a lot of differences in the ozone photolysis than a single so less OH primary production in the stronger nudging. And so then if you look at the ozone versus lifetime diagram, here is the sensitivity due to lightning that we know of. And then the green ones, so then you would have a combination of the Megan emissions. When they increase, we give you more ozone and less OH, and then also the impact of the drier atmosphere that gives you less OH, which end up decreasing OH, increasing mass and lifetime, but then at some point starting to decrease the ozone by not efficiently producing ozone, probably because of feedbacks, because of the biogenic chemistry. That's it.
Okay, thank you, Ben. I think in the interest of time, maybe we should move to the next talk. And if anyone has questions for Ben, they can ask during the break or. So next talk will be remote by Yu Yao, and I believe they're online. So if you want to start sharing your screen. And the presentation is on ion catalyzed chlorine production, and we can see your screen just fine.
Can you hear me?
Yes.
Okay. Good morning, everyone. I'm Yu Yao. I'm currently a postdoc at Cornell University, working with Matthew and Peter. Thanks for Ben and Rafa. They give a great background for my talk. So here maybe I'm easy to introduce my work now. So my talk is about ion catalyzed chlorine production using saline carbon isotope signature observations and with uncertain methane budget impacts. So the motivation of this work was based on very interesting observations of Barbados. So Barbados was an island in the downwind region of Sahara dust, and people found in the fall season in 1987. So here is the isotopic signatures of the carbon monoxide, and the gray dots are the observation, and the gray line is for the inverse model results. And they find the model cannot capture this very depleted carbon-13 carbon monoxide in the fall seasons. And what happened in 2023, and they implement mirror dust sea salt interactions with produced chlorine, which can help explain these very depleted carbon monoxide isotopic signatures. Here I made a simple schematic to show these interactions. So when mineral dust and sea salt combines, and the ion cycling between ion third and ion second can catalyze the chloride production to produce chlorine molecule and further photolysis to chlorine radical. And the chlorine radical reaction with methane will produce a very special carbon monoxide with very depleted carbon-13. So the carbon-13 is around minus 100 per mil. The typical carbon-13 carbon monoxide is around minus 28. So this is a very special carbon monoxide. However, the study is not that simple. As mentioned by Ben and Raffel, the chlorine radicals not only react with methane, but it can also destroy ozone, and ozone is a major source for hydroxyl radical. And the reaction methane with hydroxyl radical is a dominant chemical sink for methane. So methane not only reacts methane, but also destroy ozone. According to a study by Li and Maiden in 2023, they find additional chlorine need to reach a certain threshold to really result in the reduced methane lifetime. And they find the threshold is around 90 teragram per year. And then if it's over this threshold, we can see the methane reduced with increased chlorine molecules. So in order to better understand these reactions, we use this carbon model framework with several new figures. The first is a solid hydrogen chemistry, as mentioned by Raffel 30 minutes ago. And also we incorporate the solid ion process, which is the MIMI scheme and was developed by Hamilton in 2019, which can track the ion from different sources, such as dust and endogenous combustion, and also by spinning. And it can also simulate the aging process of the ion and to check the solubility of the ion. And then in this work, we further cover two ion catalyzed chlorine process to understand the chlorine production process. So here introduced the two MDSA, the mineral dust sea salt schemes in this work. The first one is we had a Maiden scheme. So this scheme parameterized the chlorine production rates based on soluble mixing ratio, ion mixing ratio, and solar intensity. This reaction limited at surface layer, and in the environment with sea salt mixing ratio larger than 10 to minus 9 kilogram per kilogram. This parameterization was applied by Verhagen in 2023 in using CS in version 1, and also by Maiden in 2024 using version 2, but offline of the soluble ion process. The second parameterization was the TEN scheme, which parameterized the chlorine production rates based on the soluble ion molality, chloride molality, and nitrogen dioxide photolysis, and aerosol surface area. So since they have several constraints, so they do not limit this reaction over the surface and also the sea salt condition. Both parameterizations are based on the chamber study by Wittmer in 2015. So the TEN parameterization was applied in geoscan and was evaluated in over a continent site in northern China. So based on these two parameterizations, we did two group simulations. Both are using a 1D resolution, and the simulation period is 1984 to 1989, where we have the CO isotopic observations. For the methane, we use the fixed lower boundary condition, and we are using the emission for CMIP6. For the first group simulation, we are simulating the effects on DSA at the current ion condition, which is around 2 telegram ion per year. So we have three simulations, one without MDSA, the other with the Verhagen Maiden scheme, and the third one with TEN scheme. We also have another group simulation where ion, 100 times of ion are emitted over the ocean, which is around 200 teragram of ion are emitted. So we did two simulations in this scenario, one using the Verhagen Maiden MDSA scheme, the other using the TEN scheme. Now, let's first look at the results for the chlorine production rates in the current ion condition. So the two spatial maps shows the chlorine production rate using the Verhagen Maiden scheme and the TEN scheme. So here we find if using Verhagen Maiden scheme, the chlorine production rates are higher over the ocean region, while in TEN scheme is over the coastal region. We further look at two sites, Barbados and China, to see the monthly variations. Here the first law is for the Verhagen Maiden scheme simulated results, and second law is for TEN simulation. And different color are for the different islands. The blue color is for China side and the orange color is for Barbados. So we can find in both simulations, they simulated higher chlorine production rates over China is because of the higher solid ion mixing ratio and higher solar intensity. And also the chlorine production rates are higher over the summer region because also of these higher values. Because of the change in the chlorine, additional chlorine production, we can see the changes in the CO isotopic signatures. So here is the equation we use to calculate the CO isotopic signatures due to the additional chlorine production from MDSA. Due to time limitation, I will not explain this equation. Feel free to ask me if you have any questions about this equation. So here, this figure shows the model simulated and observed CO, the third carbon-13 CO over two sites, Barbados and Tenerife. So the black dot is for the observation over Barbados, and the red triangle is for the observations over Tenerife. Here, the inverse model results without MDSA was in the gray line, and we can find this inverse model cannot capture this very depleted carbon-13 signals in the summer and autumn seasons in 1997. But if include the web maiden skin and tan skin, these very depleted signals can be well captured. We also further calculate the shift of the carbon-13 signatures between these two sites, Barbados and Tenerife. So here the black line is for the shift from the observation, and different color in the third subplots are from different simulations. So here we can find, using the term parameterization, this seasonal cycle in the carbon monoxide isotope signatures are well captured. But if using the happens model, which is CSM version 1, and also the we have maiden scheme with the CSM version 2, they cannot well capture these very seasonal cycles. So we also analyze the effects on ozone and OH distribution. Here, the first column is for the control case simulated ozone and OH. And the second column is between the difference between the we have maiden skin and control case. And the third column is for the difference between tan skin and control skin. So here we can find both MDSA parameterization will reduce the ozone and the OH. And for the parameterization using we have a maiden skin, the changes, especially the decrease, are most obvious over the ocean region, while using tan skin, the changes are more obvious over the coastal region. So this spatial pattern is consistent with the chlorine production rates we discussed before. Now we also check the oxidation rates of this additional chlorine. So because of the additional chlorine from the parameterizations, we can see, so here the first law is for the reaction between methane and chlorine. So it increased 2 times in the we have maiden skin and is over 7 times in tan skin. But OH decreased correspondingly, but the ratio is much smaller, it's around less than 1% globally. So the resulting total chemical loss with this additional chlorine is around less than 1% globally. We can also see the changes in the reaction with chlorine and ozone reaction, so which also increase over 2 times if using web maiden parameterization, and is over 5 times if using tan parameterization. So with these changes, we are expecting changes in methane budget. So here shows the methane budget if in the current ion condition. The first column shows the additional chlorine from the mineral dust salt parameterization, and the second column shows the methane reaction with chlorine budget, and the third column shows the methane reaction with OH, and the fourth column shows the net loss due to the additional chlorine produced from the MDSA. So here we find if using web maiden scheme, the net methane chemical loss was reduced to 10 grams, so it will increase methane. But for the parameterization using tan skin, the methane loss increased 1 teragram per year. So we also analyze the case if there are more than 200 teragram of iron are emitted over the ocean, and we find that much more chlorine produced, and also the methane reaction with chlorine was also much stronger, and also the corresponding reduced in methane reaction with OH, As a result, we find if using Webb maiden scheme, this additional 200 teragram iron will result in additional 22 teragram meson loss. And for if using 10 scheme, the additional loss is only 5 teragram. So it's also reasonable because 10 parameterization has more constraints. So adding iron will not linearly increase the meson loss in this parameterization. So the takeaways from this work that we applied two different schemes from the same chamber study, which is Whitmer's 2015 chamber experiment. And we find similar carbon monoxide isotopic effects at the Barbados and Tenerife. And we find meson respond modestly using at current iron environment less than 2 teragram per year changes. But if we add the additional 200 teragram iron of the ocean, you can see substantial increase meson loss if using Webb maiden scheme. But if using 10 scheme, the loss is less small, it's only 5 teragram per year. And so for the future works, we have two main goals. The first, we want to better understand the mineral dust chlorine production rates. So we are planning to use a particle resolve model, which can have the aerosodynamics module, PaLM-C, and aerosochemistry mosaic, and aqueous chemistry Capron to better understand at which size range is the reaction most efficient, and what are the aerosol species, such as sulfate and organic matter, will affect these chlorine production rates. And we will also compare with the results from some field measurements. So we are collaborating with John, Alex, Dan, and Cassie on this project. And also the current way calculate the CO isotopic signatures are quite simplified. So as we know, different CO sources have different CO isotopic signatures. So we are collaborating with Ben and also John to implement the CO process and also CO tech models to better understand the CO isotopic signatures. So with that, I'm happy to answer questions.
Okay, are there any questions?
I have a question. Yeah. So really nice talk, Jude.
Thank you.
So really interesting to see how, depending on the pH parameterization or the chamber parameterization, the impact of these enhanced chlorine iron levels will change the loss of methane. But I was more focused on slide 9, I think it was, when you showed the Barbados and the Tenerife seasonality, I mean the year variation, because most of this process is related on the outflow of the Sahara dust. Okay, so did you compare model results with Tenerife observations? Because I only see there the comparison with Barbados on the model.
Yeah, that's a good question. So that's the reason why we use the shift between the sites, because the inverse model are very simplified. They only have a global value for all locations. So they do not specify it's over Barbados and Tenerife. So that's the reason we want to develop our own simplified CO tech model, which can have the CO isotopic signatures over both sides.
Okay. Okay.
Yeah, there are also more observations over this site. So I think from Thomas Group, they now have more recent data of the isotopic signatures where we can use our model to compare. But this data are based on 20 years ago, so we need to better represent this process.
Thank you. Thank you very much.
Thank you.
Bruce has a question, but in the interest of time, I think we should move on. Maybe you can discuss in the chat or offline.
Yeah, sure.
Okay, thank you.
Thank you.
Next presentation will be given by Ari Feinberg, and the title is Shifts in Atmospheric Composition since a Pre-Industrial Modified the Transport and Deposition of Mercury. And do you want to go ahead and share your screen?
Yeah. Okay. Okay. So I'm guessing you see this now?
Yes.
Okay, perfect. So hi, everyone. My name is Ari Feinberg. I'm a scientist working in the Spanish National Research Council in Madrid. And so I'll take you in this talk to the world of atmospheric mercury in CESM. So the mercury is emitted to the atmosphere by a number of different sources. First of all, you have anthropogenic sources of mercury, which include fossil fuel combustion and gold mining, as well as mercury's other industrial uses of mercury. You have a small source from geogenic sources like volcanoes, and then you have re-emissions of mercury from the ocean, as well as from soils. And so the main species of mercury that's emitted is elemental mercury. This is a highly volatile. It's also insoluble and quite long-lived in the atmosphere, so around 6 months. So this species is the one that can be transported globally. And then however, this species can be oxidized mainly by bromine and OH radicals to form oxidized mercury species. And so it's a two-step oxidation where first it forms mercury 1, and then this can proceed via reaction with ozone to mercury 2. And so once the stable mercury 2 species are formed, these are soluble species which can then be deposited through scavenging by rainfall. So once mercury is deposited, that's where especially in aquatic environments, it can be methylated into a toxic substance called methylmercury. This bioaccumulates in the marine food chain, and that's really where the risk to humans come in, because we tend to eat fish that are quite high up in the food chain, like tuna. And so just to give you an idea of the impact by numbers, so really the mercury issue started to come into global awareness with the Minamata disease, which started in the 1950s in a bay in Japan, where mercury was directly released by a chemical factory. And this led to over 10,000 victims at that time. And then thinking about the chronic impacts of mercury, so in a study estimated the global health cost of the neurological and cardiovascular risks associated with mercury exposure, and this number came out to around $117 billion per year. So this is quite an important issue, and as you can see, the atmospheric transport of mercury is really the way that this contaminant gets spread out around the globe. So in my project at the SEEK, what we were interested in looking at is diving more into the atmospheric chemistry of mercury. So looking at this simplified scheme, what we saw is that you have different oxidants involved, like OH, like ozone, and like carbon monoxide. And if we think about how these compounds have changed over time, for example, these plots from CMIP6 papers showing the trends in ozone and OH, there's been quite a lot of differences in the atmospheric chemistry between pre-industrial and present day. However, no one's really looked into this issue for mercury, whether the oxidation of mercury has changed over that time. And most modeling studies until now that have looked at past periods have just assumed the same chemistry for different periods. And so that's what we're interested in looking into with WACCM. So the WACCM model includes a full mercury scheme. And this is, there are other atmospheric mercury models, but this model is unique in that it's a chemistry climate model. The other ones are all chemistry transport models. And as well that we have the state-of-the-art short-lived halogen chemistry, which Rafa talked about earlier. So for today, I'll be talking about my simulations, which were done at 1.9 by 2.5 resolution in the WACCM model. So the methods that we use for this is to look at the differences in the mercury redox chemistry between pre-industrial and present day. We use the emissions from CMIP6 and the short-lived halogens following Rafa's latest work. And then the mercury emissions we get from different emissions inventories that are available. And so this shows an evaluation of the model for present day. So these are the two main measured mercuries, the two main types of mercury measurements that we have. So the top shows the elemental mercury concentrations, and then the bottom shows wet deposition measurements of mercury. And we're relatively happy with the agreement that's shown. This is sort of the standard levels of agreement that other mercury models tend to show. So given that, we're confident that this model is showing a good representation of the current day mercury cycle. And so what we then were looking at is the differences in the chemistry between pre-industrial and current times. So this is the map. The map that I'm showing here is showing the change in the tropospheric elemental mercury chemical lifetime between the pre-industrial and present day. And so this is considering chemical lifetime in tropospheric columns, which are calculated based on the elemental mercury burden and the net oxidation flux of elemental mercury. And so these blue areas show all the areas where mercury oxidation is faster in present day compared to pre-industrial. And so in the northern hemisphere, especially in the tropics and subtropics, this is where the oxidation chemistry is speeding up. On the other side, these red areas, especially in the southern mid-latitudes, that's showing where the elemental mercury oxidation has become slower in pre-industrial compared to present day. And so this was interesting for us to see because overall, globally, there's not a substantial difference in the tropospheric lifetime of mercury between these two periods. However, there's quite a lot of differences spatially in where this oxidation is occurring. And so I'm going to walk you through the mechanisms that we think are at play for what's driving these different changes in the mercury chemistry in these different locations. And so first, for the southern hemisphere, where we saw that mercury oxidation is becoming slower, what you have here is that the bromine atom, which is one of the main oxidants of mercury, especially in this region, in the southern hemisphere where you have high Br concentrations, between pre-industrial and present day, Br atoms decrease in the troposphere. And this is because you have more ozone. And so the ozone will convert atomic Br into BRO, as well as you have more anthropogenic contaminants that will convert this BRO and Br into reservoir BRY species. And so basically what's happening here is that this bromine is being pushed more into unreactive species and away from this Br, which would react with the elemental mercury. In the northern hemisphere, especially in the tropics and subtropics, you have other mechanisms which become more important, and this is because the OH concentrations tend to be higher in the tropics and subtropics, and as well the ozone increases more in the northern hemisphere. And so here these increases in OH, what they do is that this OH channel of oxidation is enhanced in the northern hemisphere, and then the increases in ozone, they play a role here in step 3, where ozone reacts with these mercury 1 species to form the more stable mercury 2 species. And so really what ozone plays a role in all 3 of these mechanisms, but in mechanism 2 and 3, ozone is enhancing mercury oxidation, whereas in mechanism 1, by reacting with Br to form BRO, ozone is decelerating mercury oxidation. And so this is kind of the first time that someone has talked about these that we've been able to show these compensating effects that ozone has on mercury oxidation. And so that was all just about the lifetime differences. But for mercury, what really matters is the impacts on ecosystems. And so where this mercury is going to be deposited out from the atmosphere into ecosystems. And so the map that I'm showing here shows the deposition differences between pre-industrial and present day, isolating the impact of atmospheric composition changes alone. And so here we've nudged both simulations so that the dynamics are similar, so that we're able to isolate the signal only from the chemistry. And as well, I run with the same emissions in both periods, just to isolate alone the effect of chemistry. And so what we see is that the red areas are where you have now more mercury deposition. So in that area where we saw the chemistry speeding up, and because more mercury gets deposited there in the tropics and subtropics, you have less mercury deposited in the southern mid-latitudes. So when we looked at this map, it kind of gave a bit of deja vu, because there was another paper that came out last year from Lee et al., which showed where the methylmercury that we get in our diet comes from. And so what they found is that the tropics and subtropics are key areas because that's where you have methylation hotspots of mercury. And as well, that's where the most important tuna fisheries are. And so if we combine these maps together, so these gray stippled areas now show those key areas for methylmercury dietary inputs. Well, what I want to highlight here is that in these key methylmercury areas, the deposition increases in present day by around 15% and up to 30% in certain of these regions. So apart from what's been known that anthropogenic mercury emissions are raising the risk for mercury exposure. At the same time, atmospheric chemistry changes. This is what's really new here. That atmospheric chemistry changes have enhanced the deposition of mercury into tropical and subtropical oceans, and this is another factor which is raising the risk of mercury exposure. I'll just briefly touch on this point. So another implication that this work might have in comparing the mercury lifetime in pre-industrial and present day is that other studies analyze mercury in natural archives like ice cores, peat cores, lake sediments, and often they assume that there's been the same transport of mercury in pre-industrial as well as present day. However, what we can see here is that in present day, you now have less mercury, which is reaching. So the mercury is less easily transported from the northern hemisphere into, for example, Antarctica, and so this could affect how you interpret ice core measurements from Antarctica, for example, for the pre-industrial period. So as a summary, what we've seen is that these different changes in atmospheric composition between pre-industrial and present day have changed both what oxidation pathway is more favored for elemental mercury, as well as the overall lifetime of mercury and the patterns of deposition, which can impact health. But I think I'm excited about this because it's just the start of starting to think about how chemistry in different periods might have affected measurements that we've made of mercury. So, for example, thinking about recent trends in atmospheric mercury, this is an example showing measured trends in Eastern North America, and these have been decreasing over the past few decades. And it doesn't really match well with what how we think emissions are changing. And so I wonder how much chemistry has played a role in these recent changes in the elemental mercury concentrations in air. And as well on a wider timescale, thinking about in past periods, mercury is often used as a proxy for volcanic emissions from sediment cores. But we know that the atmospheric composition in these periods is quite different. And so thinking about how mercury transport in the atmosphere could have changed in these different periods will be important for interpreting these records. So I'll end there. This study was recently accepted in AGU Advances, so it should be out soon. And I'd just like to acknowledge the funding for this project from Marie Curie Fellowship, as well as, of course, the support from NCAR for computing and all the researchers involved in the study and in my group. Thank you very much.
Thank you. Are there any questions?
I have a conceptual question. That was great. Thank you. I don't know much about mercury, but can we filter it out of the seawater, and can we use this kind of a simulation to work out how much we would need to filter out of seawater?
I think that's it's very challenging because the concentrations are too low in seawater to really be able to filter it out efficiently. So I mean, in very polluted areas, like in for example, in former mining areas which have high mercury concentrations, they can do phytoremediation to take some of the mercury out of soils, for example. But I think in seawater, no technology exists yet to do that.
Thanks.
If there's no other questions.
All right, welcome back from the break. We're going to get started so we don't get too far behind time. Our first talk is by Wei Wang, who is going to be talking about plume rise and wildfires. Can you put it in full screen, please?
Yeah.
Great. All right, go ahead.
Okay. Hello, everyone. Today I'm going to talk about the effects of plume rise on long-range transport of wildfire aerosols and the Arctic clouds using the music carbon zero. Wildfires emit gases, aerosols, and water vapor near the surface or at higher altitudes, depending on whether the fires are in smoldering or in flaming phases. These different injection heads can affect the transport and the lifetime of aerosols, which further affect the aerosol cloud radiation interactions. A recent study showed that when wildfire aerosols are transported to the Arctic from boreal region, they could reduce CS loss and Arctic warming. So despite the importance of the injection heads, currently few global climate models calculate the vertical profiles of biomass burning aerosol emissions. So in this study, we will incorporate a plume rise model to the NCAR Community Earth System Model 1 and 2 and investigate its effects on long-range transport of wildfire aerosols and the Arctic clouds. So the default model used in this study is the multi-scale infrastructure for chemistry and the aerosols, or the music carbon zero. It's a configuration of CAM6 CAM in CSM 2.2. It features extensive chemistry mechanisms and regional refinement. Now this figure shows the variable resolution grids used in this study. The model horizontal resolution increased from 100 kilometer to 14 kilometer over the continental US. In the default model, the biomass burning emissions are at the surface. To interactively calculate the injection heads, we include the plume rise model developed by Freitas et al. In 2007 in Musica Verandero. The input for polymerized model include the fire properties and environmental conditions. The important fire properties are fire size and fire heat flux, and the ambient thermodynamic conditions are obtained from the host model, Musica Verandero. Using these two models, we conducted 2 experiments, and the difference between experiments with and without polymerize represent the effects of injection heads. And to reduce the bias in aerosol transport caused by atmospheric circulations, the horizontal winds are nudged to mirror to real analysis data in 2 experiments. The biomass burning emissions in this study are from the fire inventory from NCAR. The species include black carbon, particulate organic matter, carbon monoxide, SO2, and NOx. This panel shows the spatial distribution of biomass burning emissions of POM in July 2018 over the Western US. The shaded color shows the POM emissions, and with the resolution at 14 kilometer, the model can capture the high emission values during wildfire events. The black line represents the flood tracks during the weekend campaign in July 2018. The weekend campaign provides the observations of carbon monoxide and aerosol concentrations. So next, we will compare the model simulations with the weekend observations. Now, these 2 figures shows the median profiles of organic aerosol and carbon monoxide concentrations in weekend observation and in model results. The black line is the weekend observation, and the blue line is from the default model with biomass burning emissions at surface, and the red line is from the developed model with polymerized calculation. So the results show that the models tend to underestimate the organic and the carbon monoxide concentrations. With the polymerized, this lower bias can be further reduced at the altitude between 3 and 5 kilometers. Next, this panel shows the changes in vertical distributions of carbon monoxide concentrations over the Western North America. And the difference between 2 simulations are shown in this figure. So the polymerized can enhance the carbon monoxide concentrations at higher altitude between 4 and 12 kilometers, especially over the boreal and the Arctic region. And similarly, for the aerosol POM, near the wildfire region, the polymerized lead to a decrease in POM concentrations at lower altitude and an increase in at higher altitudes. And in the high latitude, in the boreal and Arctic regions, the POM concentrations increase due to the polymerized, which could further affect the Arctic climate. So next, we'll focus on the Arctic region. Now, this panel shows the changes in column integrated POM concentrations in the Arctic. The results show that due to the polymerized, the POM burden can increase by 25% in the Arctic region. The larger increase are mainly in the region near the northwestern and eastern Eurasia, where wildfires are frequent. as the aerosol concentrations increase, the aerosol optical depths also correspondingly increase by 7% in the Arctic. In the downstream from the boreal wildfires, the aerosol optical depth can increase by 15%. Besides this aerosol radiation interactions, the cloud properties are modified. This panel shows the response of column-integrated cloud droplet number concentrations to the increased aerosol concentrations in the Arctic. The cloud droplet number concentrations increased by 5% in the Arctic due to the plume rise. And the liquid water pass can increase by about 1% in the Arctic. So as the cloud properties are modified, the shortwave cloud faulting are changed, as shown in this panel. The blue color means that the cloud faulting has a cooling effects, and the shortwave cloud faulting decreased by 0.32 watt per square meter in the Arctic. At the surface, the radiative flux can decrease by 0.78 watt per meter square, which can further affect the surface energy balance and the Arctic warming. So in summary, the plume rise model developed by Freitas et al. In 2007 is included in variable resolution CSM 2.2 to interactively calculate the vertical distribution of biomass burning emissions of aerosols and gases. In July 2018, compared to simulations with biomass burning emissions at the surface, the plume rise enhanced the transport of POM to the Arctic, where the POM concentrations increased by 25%. And in the Arctic, the cloud droplet number concentrations increased by 5%, and the shortwave cloud faulting decreased by 0.32 watt per square meter, which can further affect the surface energy balance and Arctic warming. And considering that the black carbon deposition in snow can reduce the snow albedo and enhance the Arctic warming, the snow darkening effect of wildfire aerosols will be further examined in the future. That's all. Thanks.
Thank you. This is exciting to have interactive plume rise implemented in the model, and we have time for questions.
Can you go back to the slide where you compare the plume rise with surface with observations, vertical profile one? Yeah, this one. So it looks like the plume rise doesn't really affect the profile all that much.
Yes.
Do they have the same amount of emission? Is this distributed vertically differently?
Yeah, the total amount are the same, but the vertical distribution are different.
So it looks like the emission is low, or because at the surface it's lower than the observation.
Yeah. I think the plume rise model still needs some tuning process, because there are a lot of parameters should be tuned according to the host model. So I will keep working on this.
Okay. Yeah. Thank you. I just thought I would expect to see some profile changes.
Yeah.
Right.
Just related to that, but this is a aircraft measurement versus a big grid cell. So do you compensate the grid cell concentration versus air?
Could you repeat the question?
The measurements are the points from the aircraft, right?
Yeah, yeah.
Values are from the grid cell of the model, which is much larger than what aircraft sees. So I don't know if it's easy to compare apple to apple.
Oh yeah, yeah. That's a problem. I used the flight track output in the model. So it is a issue about this. I admit that. Yeah.
Have you considered comparing to like satellite measurements from say MOPIT for carbon monoxide as well?
The satellite data. Yeah. Yes. Yeah. I will use the satellite data. Yeah.
That could help, like to your point that the plume could be missed by the grid box potentially. It could be misplaced, and so be one reason that you're getting.
Sure. I'm not familiar with the gases. I focus on the aerosols, so I will working on this part on the carbon monoxide observations. Yeah, thanks.
Any other questions? Yeah, I mean, there were obviously differences between the two simulations in the transport downwind. So there are profile differences somewhere.
Yeah.
Great. Okay, let's move on. Thank you again. And our second talk of this session is Judy New, looking at droplet number concentration. Judy, are you? Sorry. Do you want? First time. Okay, maybe that would be better. Right? Yeah, I can also write here. This is the first. Okay, I think I have it sharing here now. It might take a little while. Do you want to sit at my position so you can see the screen, or you can see it? You can actually see it on this screen. Sorry.
So my name is Qing Liu. I am a PhD student from the University of Oklahoma and have been visiting NCAR ever since 2023. The work that I will be showing today is work done with Christina McCloskey from CDD and all of the co-authors here, which will be about observation-oriented cloud condensation nuclear modification under the Southern Ocean using the Chem6 model. So this is a quick introduction of the motivation of this study. Here on this figure, Mallet et al. 2023 pointing out that there are, in general, bias over the Austrian summertime of surface incoming shortwave radiation. you can see this is simulation minus observation. Over the Southern Ocean, it's in general red color, which representing an overestimation of the surface incoming shortwave solar radiation. In other words, this can be related to potentially a non-reflective cloud. What does the observation say? So this is pure observation data on the right. Climatology observation using satellite data showing the Arctic clouds over this region in the season is actually very bright with really high number of cloud droplet concentration in the which might be the reason of this bias in the model. We can further show that on the right-hand figure in this slide, the bias of CCN is shown as a function of latitude. So we do see the relative bias here defined as model minus observation over observation in the unit of 100%. So over the South Southern Ocean, so south of 55 degree, the relative bias is close to negative 100% almost all through this region. So we're connecting the bias of radiation to the bias of cloud droplet number concentration to the number of the cloud condensation nuclei, which is aerosol, the water condensed onto form clouds. So what is by nature happening in this region over the season? I summarizing them into the scheme figure. Method A and method B. Method B is about primary CCN. So the sea spray emission from open water got activated as cloud condensation nuclei when it got transported in the air. While secondary CCN have lots of complication over here, but the pathway in Chem 6 includes the open surface emission from the ocean of the gas dimethyl sulfide, which got synoptic uplifted and then went through all the way from the gas to the sulfate and then through entrainment to surface cloud condensation nuclei as well. So between the two pathways, we are having this bias identification of different CCN type. So this is a paper published in 2025 talking about, not just the season, not just latitude, the bias of CCN is very well significant, but also the seasonality is not captured by the model as well. So on the right, I showed the CCN supersaturation spectral over NSL North Southern Ocean in November and the South Southern Ocean SSL in February. Given the number of CCN on the X and the supersaturation on the Y, the spectral of CCN really shows the type of CCN where it shows the capability of the aerosols absorbing water from this ambient environment. So with this black line from the observation on the ship, this semi-vertical shows that at probably 0.2%, all of the group of aerosols are actually activated already. While for the observation in summer over the South Southern Ocean, this really large slope shows we do need really high supersaturation to get it activated. In other words, the aerosols are less hygroscopic. So we do identify based on the spectral that although over the NSL in November, the curve are okayly simulated, but the model is overestimates the seesaw. While over the SSL in February, the curve is not captured, which is saying the CCN type is wrong, and also the amount is not well represented. This might be caused by some aerosol with low hygroscopicity. Small kappa also might be sulfate based on the observation chemistry observation figures not shown. For this comparison between the model and the observation, we're using the net run simulation of 1 degree over the Southern Ocean. Here I show the comparison. It's trying to capture apple-to-apple comparison that grabs the closest location with the closest time by the track of the ship. In this case, we have two to-do lists here based on the different pathway. The first is to check the release of sea spray at CCN, and then is to check the secondary CCN, which all the way started from the DMS emission from the surface. Tuning up the sulfate and tuning down the sea salt, does that influencing the CCN number performance over there? The way I did is very simple. I just did double, triple, and 10 times of the scale of the DMS emission. this is the result. Here I showed the scatter plot of the model on the Y, observation on the X. The color is by region, so gray is between 44 to 50. The red is NSL, blue is SSL. We do see after the change from the emission scale of the 10-meter wind speed, its power law efficient from 3.41 to 2.8 leads into real improvement, primary of the red color, which is NSL. While the blue color does have a little bit of improvement, but it's not that much, which might be caused by a substantial sulfate south of 55 degrees. If we tuning up the sulfate, this is the sensitivity test default run on the left, the doubling on the middle, the tripling on the right. We do see the curve of the dashed right line, which is from the model, is shifting one by one to the right. However, it's still underestimating the CCN in this general case when the DMS scale is very high in the deep summer. How does it influence on clouds? Here, this is histogram of cloud number droplet from LiDAR and radar combined retrieval. From the model in black, from the observation in black, from the model in yellow, from the base run on the left, from the updated run on the right. This is combined updates of CSAT and sulfate. We do see the change of mode here, that the mode from the updated run is more close to the observed mode here. However, there are still some scenario here where the ND is super high from the observation data, but it's not captured by the model. For radiation-wise, we're trying to fix this bias identified in this model using the top of atmosphere shortwave cloud radiative forcing with the unit of watt per meter square. You do see that the shortwave cloud forcing fact is largely blue over the Southern Ocean, shows that the updates actually makes the clouds brighter in this setting up. I want to acknowledge all the institutions and the funding agencies for this study. In general, we are bridging the CSM simulation and the observation through these two pathways to change of CCN and then into cloud droplet to shortwave cloud forcing and eventually to an energy budget. With the simulation, we identify the bias and then using observation to guide the modification of the CAM6, including the shape-based observation of CCN and the LiDAR radar retrieval of cloud droplet and the satellite retrieval of cloud forcing. With that, I will be stopping here for any question and feedback. Thanks. Thank you. Other questions?
Yeah, I have a question or a comment. Actually, I think it was in this meeting last year that Julián Villamayor, a colleague working with us on the SLH implementation in CSM, he also implemented emission of methane thiol. Okay, so which has basically two effects. One is to add additional sulfate or SO2 to the atmosphere, and another one is that increases the DMS lifetime, particularly in the Southern Ocean.
Okay.
So perhaps including those type of emissions instead of ×2, ×3 of DMS could be another source of SO2 to the atmosphere.
Yeah, that is a very good point. I was watching their slides from the same meeting last year about trying to increase the amount of sulfate in a way that is different from the original default pathway, which is a very good recommendation. It just takes some time to add in those chemistry in the model by itself, but that's really the most, I think it's closer to what is really happening in the atmosphere than just doubling, tripling to see.
Okay.
Thanks.
Any questions? I have a question about the comparison of the profile to sulfate, I think it was, this one. Yeah, so the shape of the red line looks different than the shape of the black line. Are there reasons for that, do you think?
That's also a very good question. So this is doubling, tripling only of DMS. If we do add in the decreased amount of CSAT, it would be causing the large error set, which would be 0.1 to decrease. So we actually can fix this point back left to its very close to observation scale, which is also leading into limited reduction of the small salt here. So the way if we add in the sea salt updates, it will be further left. Again, it doesn't change the shape of the curve compared to the observation. But in other words, it's saying in the observation, the small particles got produced and they developed, grew up to be large enough to get accumulated, to get activated. Well, in my way of changing the scheme, it does not have this effect. This is not about new particle formation thing. It's more about how to grow the small particles into a larger accumulation mode and also which serves the CCN here. In other words, the growth itself is an issue still, even up to this point. So the different curve shapes here really indicate that the more observation data needs to be guiding the physics behind the scene.
Time for one more question? Yes, I have a follow-up question.
Yes.
Have you tested if there's like a linear relationship, U times 2 and times 3 of the CCN?
That's also a very good point. So here in the slides, I also can also show you the times 10 scale, which is this slide. So this is not sharing mode now. And now share screen. Might need a bit of help. Back here, do presentation. Share the screen. Nice, thank you so much. Okay, so this is not a very large model, but here, if you do see on the very far end, let me remove this lap so that you would be able to see the times 10 here. Okay, pretending this is times 10 on the right. On the left, times 2, times 3, and times 10 does not have linear relationship in between. In other words, in some scenario, times 10 is actually doing the best job. So this is showing actually probably there's some, for example, the condensation of OH is playing a role in this way that is limited in the air, which is basically limiting the reaction efficiency in the whole train of so I think this is more into solvent chemistry part that investigating into the condensation of OH is kind of important in this scenario. As for the OH, as far as the DMS emission scaling is not effective, we can also see the figure of this one. Which I showed the same updates, but for the simulation of Socrates data, which is over NSL in the center. So times 2 and times 3 vertically does show that times 2 is okay for simulating the accumulation mode and also total number concentration, while times 3 is overestimating, overshooting all the way through surface to 6 kilometer high. In other words, the boom up of DMS acting differently over different region over the Southern Ocean, which also shows there's a circulation getting involved in this job. So this is not a complete take-home message saying we should modify the model in this way, but showing more maybe physics and chemistry should be involved in for the digestion. Thank you.
Thanks. Okay, let's move on. Our next speaker is Sean Michael, who'll be talking about enhancement to chemical forecasts. You're going to share your screen? Sure.
My name is Sean. I'm an associate scientist at AECOM, and we'll talk about our CSM chemical forecast system and some of the upgrades that we're making. And I'm not the only one that works on this stuff. Also, Simone, who's I think not here today, Rebecca and Lisa all provide some public forecasts. So for anybody that's not familiar with them, these are CSM chemical short to medium range forecasts that we run daily and make available to the public. And in its current configuration, what we have right now and have been running for a while is a CSM 2.2 version, which uses CAM6 and finite volume. This is the chemical component. We use WACM6 and specified dynamics. Using the TSMLT chemical mechanism. Our emissions, we're using CANS and an older version of FIN, version 1 for biomass burning. And this is a 1 degree model with 88 vertical levels. And we nudge these to GeoSFP, which gives us the ability to do a 10-day forecast. And we run these once a day, every day at 0Z. And I've been doing it daily since 2019, although I know as far back as 2014, I think we originally kind of started doing these types of forecasts. The main purpose, the way it currently gets utilized, we use them for our own WRF-Chem boundary conditions for WRF-Chem forecasts. I think there's that also use it for those purposes. There's people who use it for air quality, like Resource Watch. We've used them for field campaign planning. I have the capability of ingesting these forecasts into certain flight planning software. And then all the various papers that people use also to use our data for. And I just had an example of from the NCAR GDEX, formerly known as the Research Data Archive, showing our usage specifically from them, which is one of the places where we archive our data. So I'm curious last year, dropped off a little bit this year. Yeah. So why the switch? Really, what I'm trying to do is sync this up with the release of CSM3. So while currently the forecasts are pretty fast and stable and the outputs are all really nice and easy to work with, we are starting to get a little bit outdated. And so we've got better chemistry to utilize with CSM3. We want to increase our resolution both horizontally and vertically. And so on the left-hand side there, that's kind of what we have now. On the right-hand side, that's what we'd like it to look like, a little bit higher resolution and hopefully make it more usable than it even is currently. And the way we want to do this is in our new forecast, we want to do it kind of in 2 phases. So our phase 1, we want to start off with another 1 degree run, but using CSM3 and all the component things that we get with that. So that'll be spectral element, CAM7. We're planning on using the T1S mechanism, also CMIP7 for emissions, and then instead of bin version 1, using bin version 2.5 for biomass burning. And these will also be a 10-day nudged forecast. And then in the second phase, we want to do this, take the same configuration, but increase that from NE30 to NE120, so a 1/4 degree uniform global resolution. And depending on how expensive that ends up being, those will either be 3 or 5 day forecasts, just because I have to run these and have them out in a pretty reasonable amount of time so that they can be properly used. And just a little statistical comparison between what we have been running for quite a while versus what things are looking like. CSM3 test runs. come in at about 26,000 hours per simulated year, a little more than a year, simulated year per day. This allows us to do a 10-day forecast in about 40 minutes. And in our test case that we're doing right now, which actually it's a T4S, we do want to eventually do a T1S, just going to add 30% to these numbers, but they're basically comparable to the older specified dynamics version that we're running right now. So it actually gets us currently, at least in the T4S, we're actually slightly faster, but again, it'll be about 30% more expensive when we make that switch to T1S. And then of course, with the NE120, that's going to cost more and take longer, and we may have to adjust the forecast length down from 10 days to fit it into a reasonable amount of time. And more than likely, I'll probably run these side by side, so we'll have both. And I just wanted to take a few slides to make some comparisons with what we've had with the CSM2 version and then our CSM3 version. So this, the red lines and dots are our new configuration. The blue is the older one, our older forecast. And the left four panels there are just the profiles of ozone, seasonal climatological profiles. And on the right are Taylor diagrams. And these are using data from 2020 to 2024. And the general take-home message there is that in our older forecast, our ozone is too high. We knew about this, and I've gotten emails from people that have complained about it in the past. But our new configuration at CSM3 actually looks a lot better. Those left-hand panels, those black lines there are actually compared with ozone suns, and so it's comparing with real data. And they fall a lot closer to those ozone sun observations in the newer configuration than they do our older one. And the same on the right panels. We're a little bit, it shows a fair amount better. And this is a surface comparison using AECOM's Melodies Monet product software package. And this is comparing a different set of observations. These are surface air now observations, and this is just a single day, but pretty representative of what I've seen so far. The top panels are new CSM3 setup. The bottom is our older CSM2 setup, and it's pretty easy to see that our ozone is at the surface is closer to observations in the new one than it is the old one. And again, at the surface, in our older one, it just often comes out, the ozone's too high. And so we're in better agreement. This is the new one. This one's the T4. I would expect the T1 to be similar. We also see an improvement in the tape recorder. This is also climatological 2020 through 2024. On the far right-hand side, that's our current older forecast setup. And the third panel from the left is our CSM3 version. And our old forecast it's too wet, and I think we knew that before also. But our CSM3 version is much closer to what it should be. I think on the left-hand panel there is compared with MLS, and then Arrow 5 is the second to left. So we're much closer now to what in much closer agreement to what those show. And this is AOD, similar climatology 2020 to 2024. The left two panels are the new configuration and our older forecast configurations on the right. And in general, you want those to be, those are difference plots. So you, on the top there, so you want those to be as close to 0 as possible. And in our newer configuration, we're definitely closer than we are in the old forecast. I know Simone had mentioned that in the particular case we used that the sea salt might have been set a little low and that might contribute to that slightly, but we've done other runs though, and I think it's still going to be better than what we had previously. So some additional enhancements, everything that comes with CSM3 we'll obviously have in there. So things like the improved dust scheme, the moving mountain gravity wave scheme, which we heard about yesterday, things like MAM5, possibly TUV, that June will be talking about in a little bit, I think. And then all the other CSM3 associated upgrades. On top of that, basically the system is kind of a wrapper that allows us to pre-stage all of the inputs and run the model and post-process things automatically. And there's a bunch of updates that I'm including here that'll make that more streamlined and faster. Possibly, we're trying to figure out what to do with sea surface temperatures since we don't really have a good way to do that right now. I'm also going to include diagnostics like ADF and Melody's Monet, which I demonstrated their uses for in quite a few of my previous slides. And the long-term timeline, we're going to start with NE30. Probably in about 6 months to a year, we'll add in the NE120 quarter degree run. We'll have to do a lot of tuning to probably make that look right. And then long-term, a few years from now, hopefully it'd be nice to do a Musica version 1 type forecast. That'd be great. And these are just some resources where all this stuff is available. It's publicly available, the data from our GDACs, so we have forecast pages. And really, you could just Google search Wacom forecast and a lot of this stuff will come up. So that's all I have. Thanks for listening.
One question.
I was going to say, do you know between the CSM2 and CSM3, what is like the main reason for the forecast improvement? Or just many things.
It's just many things. The case that I used for our current forecast is pretty, and so the climatological stuff especially, it's actually a mix of a couple of different cases. About 2/3 of that is CSM 2.1. And then once we switched over to derecho, it switched to CSM2, but in general, yeah, it's just a lot of different things that's better.
Might be the vertical resolution for the upper troposphere and the stratostrope exchange.
Did you change the chemistry a lot, or
No, I don't know. The chemistry's been the same.
I was surprised of the improvement on the upper part of the vertical profile with the compression with the SONSONs. So those SONSONs are for the same period of time.
No, so they run
that's a climatologically.
Yeah, they're the climatology.
Okay.
That's actually one.
Anyhow, it improves a lot in that region, which is really hard to get it.
Is there a trend between your horizontal and the old horizontal? Do we see increase or decrease? Anyone look at it?
I don't know that we look at that. I know one of the things we want to do in the ADF is update our ozone and sun climatology.
Yeah, Melody should be able to look at the real time.
Yeah, great. And that's kind of why we use, want the ADF and Melody's Monet, because ADF gives you the climatology and Melody's Monet gives you the daily stuff, which is always actually nice to look at.
Great. Okay, we need to move on. Thank you. So our last speaker before lunch is going to be Siddharth Roop, who is online and talking about physical perturbation for that state. Would you like to share your slide, Siddharth?
Yes, I'm trying to upload it. I'm trying to share my screen. Okay.
Can you do full screen at all?
Sorry.
Can you make it full screen at all, like presentation mode?
Maybe like this is fine.
Um,
I don't see something like, I don't know, I see blank thing.
yeah, just a blank screen right now. This will work. Let's just go with this. Okay, that's good. That's good. Yep. Okay, go ahead. Thank you.
Okay. It is a bit weird. Yeah. Okay, so I'm kind of new to earth sciences. My background has mostly been into maths and mechanics. Mostly, try to solve computational problems for mechanics. So here I got a chance to start working with Environment Canada on solving mathematical problems that are relevant to earth science. And that is how I got introduced to this whole field. And I'm pretty new in here. Um, I'm coming from a standpoint of developing computational methods for CESM rather than understanding the physical parameters and stuff. So it will be my talk would be pretty generic, as in that sense of it might be too generic for CSM audience. So the motive here is if we do ensemble prediction, like we're limited by the number of samples that we can generate. They're mostly because the numerical model that we have is expensive. They have to solve a lot of physical equations. Other than that, the other problem is creating perturbations so that I can sample a lot of initial states, or rather my model could give me different stochastic predictions. So here I have some results from a paper called ForecastNet.
Are you changing the slides? We're still on the very first slide.
Oh, okay. I'm in the second slide. Oh, my bad. I don't know what is happening.
Maybe, yeah, okay. That looks good. That is the second slide.
Do you see the slide changing? Like
Yes, now.
Oh, yes.
Yeah.
Yep.
Oh, okay. I think the mode was creating some problem. Okay. So I'm starting in here again. So my motive is to create some algorithm to pot up the atmospheric state, especially something if my case is pretty high dimensional. And the problem that I face is, let's say this is an example I brought forward from ForecastNet. So they have some comparison between IFS and their model, which is ForecastNet. It is a coarser model though, but the thing to notice is for a model that requires like around 3,000 nodes, ForecastNet could produce a similar result with 1 or 2 nodes. Essentially, they want to say that machine learning models are faster, even though they take longer time to train. But for using them, it's much faster than solving PDs and solving the computational problems in the conventional methods. So that's one way to increase the sampling rate for ensemble prediction. But there's another concern that I will focus on. So we started off with this project. So the typical neural networks, they're like inefficient for large advection in the model, which is typically if I take a large time step. For example, my lead time is like, say, 1 year or something like that. The trends might have changed a lot. And it is pretty much relevant in weather applications. In order to model this long-range transport of patterns, we essentially try to introduce the semi-local engine push operator into a machine learning model so that I could easily transport things across the whole domain. We use this concept to model the whole atmosphere from Area 5 at 1 degree resolution. And these are the couple of variables that we take. And we're trying to identify this atmospheric and surface variable so that I could use it for the next prediction for the next hour or so. Then I can use auto regression to keep on predicting the future. So this is the early model that I had created. We created actually with Environment Canada, and we recently have submitted this paper to a conference, and we're kind of getting pretty competitive results. The model is kind of similar to what we get from GraphQuest or Pangu. HRES is kind of sometimes debating a lot, but these all are the trends that we get from the machine learning models. Here we have another model, like another comparison. It is directly from our paper, where we try to track this particular cyclone. And these are the different trajectories that have been predicted. Now, this gives us a motivation as in like our model is kind of deviating from the initial, track, and somehow it comes back. Maybe we're a bit lucky, but there are other tracks which like typically we expect them to, sticking to the original track in the beginning and then diverging. But there are still problems, as in like not all models are correct, right? So, I mean, there is no correct model as such. So even if I'm predicting something reasonably well, there might be some cases like there is a rare event where the trajectory could be much different, or maybe my model fails in some certain type of conditions. Like in this is an example from from paper where they're comparing Pangu weather forecast and HREF. So HREF is the numerical model, which is in blue. So this is the trajectory that it suggested, and red one is the trajectory that Pangu predicts, and black one is the real trajectory. Like in these two cases, we say that deep learning is kind of working well. But what I'm concerned about is numerical model is not bad, but still it gave a trajectory which is pretty off compared to the original trajectory. And this trajectory keeps on deviating from the original track with time. So our focus is to, if I can generate more samples for ensemble prediction, then I try to evaluate all the rare cases, as in like I can get the probability of the whole space instead of getting the probability from only few trajectories. I can get the prediction for let's say 100 or 1,000 trajectories, or maybe 10,000 trajectory. Then I can better sample the chances of the chances of probability of something happening more precisely. Now to do this, we get a motivation from generative models. So the first motivation is I can create a lot of random noises, but I can't create realistic images. So they kind of learn the mapping between the data. So by using mapping, I can create a new noise that will keep me that will start
For a
generating new
minute,
data.
could you just repeat what you just said about this slide?
Sorry?
We just lost your sound for a second. Could you just repeat what you said about this slide, please?
Okay. So the backbone of generative AI is creating a mapping between a noisy data to noisy as in like a complete noise signal to a real data. If I have 100 real data, I'll take 100 random noise and try to create a map between them. Once I know the mapping between a real data to a noise, then I understand how to transform the statistic of complex data, which could be a satellite image, to a Gaussian noise. So the benefit of this is, if I know this function, which is the mapping between noise and data, I can create many samples for the noise. So I can create a new sample for the noise, and ideally that should be creating a data that would look like a real scenario. Because it's tough for us to create real samples, but it's pretty easy for us to create noises, the Gaussian noises. So we take this thing a bit forward. So recently, there is this flow-based generative model, and those models are invertible. As in, like, if I'm training a generative model that takes in noise and gives me a new sample that looks like the real data, I can use the same trained model to take in the data as input and predict the corresponding noise signal. So this is used for creating latent Gaussian state, and that can be used for the purposes like probability sampling and stuff. But the trick that we use in here is, if I know the mapping between the Gaussian state for any image, I do not know how to put up the original image. Like, I don't know how to change this original image so that this would look like a real scenario. Like, for example, I do not know what signal to add to this particular person waving the hand so that he would move, as in a person would move, like they can move their hand, move their leg, or something like that. But what I can do is, I can keep on adding Gaussian noise on top of the Gaussian noise. They can be added, and the statistics should still remain the same. So what we do is, once we take a trained model that is trained as a generative model on the whole data set, I use the inverse formulation of the generative model to find the corresponding noisy signal. Then I add a small noise to my existing noise state, which is a Gaussian state. This sigma could be like 2% or 3%. Then I generate on this disturbed state. So I'm using my generative model now to get back the state in the real dimension or my real data space. So by changing the signal in my Gaussian state, I'm able to see something that is a change compared to the initial data sample, and that looks pretty physical. So mathematically, if I see a generative model is kind of a function, which is creating a map between X and noise. X is my data, which could be this one or any satellite image. A good thing about my generative model is I can find the inverse of that. So I can write this formula. Function of inverse of the data is same as the data. Now so X is the data. I do not know how to perturb X. But if you notice, F inverse of X, which is a transformation of the data to a Gaussian noise, is a Gaussian noise, so I can add noise. Sorry?
There's just 2 minutes left, just to let you know.
Oh, okay. Yeah, so so I can add a noise to this Gaussian state, and essentially I know how to perturb this inner function. and hence the resultant of this net function would be giving me a disturbance onto the X. So I can easily mathematically formulate the disturbance in X by perturbing the inner sample. And I can calculate the physical perturbation by the difference between the actual state and the recovered state. So this is the concept behind it. I'll show you some results. Like we trained some initial toy examples where we had like different digits in an image, and these are like handwritten digits. We use generative model to create perturbations, which are also looking like handwritten images, and the trends, like the perturbation trends, are similar to how a handwritten pattern would change. Like things could get curved, the size and shapes could change. And we use that on 5-degree ERA 5 dataset, and that is working well. And what we have in plan is to work on like 1-degree dataset. And this is a sample that, sorry, I do not remember the exact variable that we are perturbing here. So this particular data is being perturbed to this particular state. And this is the actual perturbation, that is the physical perturbation that happened. And so the motive is to create an upgrade to our current AI model, which is Paradise 2.0, with an unanswerable prediction facility, which could easily sample 500 to 1,000 ensemble members, so that we could be more concrete on the basis of the probabilistic prediction. And that's all I have. And I would like to thank my collaborators. And I'd appreciate if there is any question, and I'll be happy to collaborate with and learn more about CSM.
Great, thanks. Are there any quick questions before we head to lunch? I have a really quick question. Do you think this kind of forecasting is like complementary to something like an Earth system model forecast, or like can each system learn from one another? Is there something you'd like to say regarding that?
So this kind of model, like the model is generalizable. So we can use this algorithm for, yesterday we heard two talks on PPE, where we put up the initial state and create model, and those applications were different. So we can use this model for all different random applications, be it aerosols, or be it like any gaseous state that we want to perturb. Like for example, I have a cloud of carbon dioxide, and I want to know how they would diffuse and stuff. And based on the exact spread in the atmosphere, they'll give a different prediction in time. So I can use it for perturbing, let's say, gases. I can use it for perturbing oceans. I can use it for perturbing vegetations and almost all of them.
Great.
Yeah.
Okay, thank you. And thanks everybody in this session again. We now have lunch until 1 p.m. So back in this room at 1 p.m. Although we still went over most of the first.
How are you doing? I'm back at the university. I've been kind of a circuit every year.
You'll have negative time, actually.
Yeah.